It's really a pleasure for me to be here. It's my first time in Stockholm, so it's a double pleasure. And Lufthansa is striking, so I got stranded in Frankfurt, but thankfully we made it here on time. So everything's good. So what I want to talk about today is some ideas that we've been working on in our group, and other people, of course, have been working on as well, where our goal is to try and build A to D converters that sample signals at rates that are far lower than the Nyquist rate. So that will be the main idea. We'll try to go through both the theory and the applications, and we'll see hardware as well. So we'll see that these ideas aren't only theoretical ideas, but they can actually be done in practice. And I'll show some examples of the hardware so that you can see that this is not only theory, but it could actually lead to practical applications. And we're working on this technology together with different companies in Israel as well. So let's start from the very basics. So there's a really nice song by Judy Gorman, who's not an engineer, so I don't know what she means by this song, but it's very good for this slide. So she sings about being an analog girl in a digital world, which very nicely captures the essence of sampling. Because what we're going to be focusing on are signals that are analog, for example, radar, music, images. But what we want is to extract information from these signals, and we're going to extract them in a digital way. And that's because, as we all know, right, we prefer, nowadays at least, to do things digitally because of the flexibility and the algorithmic power offered in the digital domain. But of course, if we want to be able to go from the analog domain to the digital domain without destroying the information in the signal, we have to do it in a way that preserves the information. And as we all know, the way of doing that, at least today in essentially all A to D converters that exist, is the well-known Shannon-Nyquist theorem. So what does this theorem say? It says that you have to sample the signal at twice the highest frequency in the signal. Okay, now this is a very important theorem. Of course, it made a tremendous impact. Due to this theorem, we have ADCs, and we're able to do digital processing. But the problem is that today, if we look at modern applications, of course, we become greedy. So if we know how to do something, we want to do more, right? And therefore, we try to process signals that have wider and wider bandwidth. And this leads to two main problems. The first is that the sampling rate becomes very, very high. And in fact, in many applications, for example, in radar, it exceeds the capabilities of ADC technology. So we have signals that have a bandwidth of, let's say, several gigahertz, where in order to get a sampler at that rate, we have to use very, very excessive hardware solutions. And in fact, that sometimes we just can't sample at that rate, and we have to lose information by using anti-aliasing filters. So one problem is the hardware problem of trying to build A to D converters at these high rates. The other problem is actually a DSP problem. So it used to be that we would think of analog as being hard and DSP as being essentially free. But today, that's no longer true. So in many applications today, what we find is that the DSP rates become so high because of the high sampling rates that we can't keep up with them anymore. Or in other words, trying to keep up with them requires a lot of power and consumes a lot of heat. So we have both the analog problem of actually just sampling at the rates and the DSP problem of processing the data that's coming to us at these rates. So essentially, this basic block of the ADC, which we essentially take for granted, is actually the bottleneck in many DSP applications today. And that's what we want to target in our talk today. Okay, so what happens today? I mean, we have ADCs, right? We do digital processing, so how do we do it today? So essentially today we have what I call the separation theorem. And this separation theorem is about people, okay, not channels and codes, for those of you who are familiar with the separation theorem from coding theory. So in this separation theory, we have two types of peoples. We have circuit design experts, and these are people that essentially work very hard to build circuits that could give us samples at higher and higher rates and acquire higher and higher bandwidths. So they're trying as hard as they can to give us more bits per second. And they use very sophisticated methods in order to do that. So on one side of the room, we have these circuit design experts. On the other side of the room, and usually they're behind a big brick wall so that they don't talk to each other, we have the DSP, or the machine learning people. And what these people do, and I'm among these people, what we normally do is we get the data from the ADC. We don't really care, right, how the people gave us the data, as long as we have this Nyquist rate sample data. And then we have to go ahead and process the data. And the first thing we do today in essentially any application is we throw away the data. Now, of course, we don't take it and throw it away in an aggressive way. We do it in some sort of smart way. So this could come under different names, right? We do dimensionality reduction, feature extraction, parameter estimation. But all of these are nice words for saying that actually we don't need all of the data. We could reduce its dimensionality before we do the processing. So we invest a lot of power and time in order to try and reduce the dimensionality of the data. Okay, so if you now take a holistic point of view and you view these two processes together, right, you take down that wall, what you see is happening that on one end, there's people investing a lot of time and power in getting us high rate data, and then we're investing a lot of time and power in order to throw away that high rate data. Okay, so really that doesn't make sense, right? Really you'd like to combine these blocks and say that if at the end you could get away with throwing away the data, if at the end you could do dimensionality reduction, then why not do it at the beginning? Why not start off by only sampling the data that we need, instead of sampling at a high rate and then throwing it away? Okay, so this is really the punchline of what we want to show today. Could we, and the answer is yes, at least in certain cases, sample the data in such a way that we're doing the dimensionality reduction together with the sampling method? So we want to develop the theory for that, and we also want to make sure that this is viable. So we don't only want theory, but we want actual circuits that could do this, that could do it in a robust way and could do it in a generic way, so that we don't have to go ahead and build a separate ADC for every specific application. So this is really the goal of the talk today. What we want to talk about is how we could exploit structure in analog data in order to reduce sampling rate. Now, people always get kind of alarmed when I say exploiting structure, right? Because then they say, well, then it's not generic, right? The nice thing about Shannon-Nyquist is that it's generic. But first of all, Shannon-Nyquist exploits structure too. It exploits that the signal is band limited. That's a type of structure. Furthermore, in our DSP algorithms, we definitely exploit structure, because if we didn't, then we wouldn't be able to do dimensionality reduction. The only thing is that in many DSP algorithms, it's not made explicit. So in a lot of these machine learning algorithms, for example, there's no kind of part of the paper that says, now we're going to assume that the data has this and this structure. But it is assuming that, otherwise the methods wouldn't work. So the only thing we're doing is making more explicit the types of ideas that people are using anyway. So we're not really adding more constraints to the problem, we're just making them explicit and trying to exploit them further up the chain. Instead of at the end, we want to exploit them all the way at the beginning. Okay, so that's the main idea. So we're going to be focusing on sampling rate, which of course has to do with power consumption, storage, right? If I reduce the rate, I'll reduce the power on the storage. But I do want to point out, and we'll talk very briefly about this, that if you know how to reduce sampling rate by exploiting structure, you could get other benefits as well. So you could exploit the structure, for example, to get better resolution, to get better denoising capabilities. Okay, that's the other side of the story. So in a nutshell, if I could nicely characterize the structure and develop tools for exploiting the structure in the analog domain, I could get lower power, better resolution, better denoising capabilities. Okay, and essentially I'm getting this for free just by exploiting the structure that's in the data anyway. Okay, so what I'm going to do in the talk, I'm not going to go too much through the mathematical details because those tend to get quite involved, and you could find them in the references. I hope that you'll leave here getting at least the essential idea. So what I want to do is kind of make it more on a tutorial level, give the main ideas and concepts, and we'll go through a variety of applications depending on time and questions to show kind of how these ideas could be translated into real systems. So here's the outline for the rest of the talk. I'm going to start by giving motivation, okay? And this will take, at least 10 minutes, going through some applications and convincing you that it is natural to use structure in many applications. So these aren't artificial mathematical ideas that I'm putting onto problems, but structure that already exists in many problems that we're interested in. We'll then talk more specifically about the type of classes we're going to be looking at, and then we'll introduce a paradigm that I call sampling. So sampling is really a combination of compression and sampling that we do simultaneously. So we sample and compress or reduce dimensionality at the same time. Okay, so this will be kind of the theoretical tools, and then depending on time, we're going to go through some concrete applications. So we'll see applications to cognitive radio, to time delay estimation, ultrasound, radar, and then depending on time, we'll go a little bit more into the ultrasound application and talk about how not only you could reduce sampling rate, but you could actually do processes such as beamforming in the compressed domain, so all of the processing could be done at the low rate as well. And finally, we'll talk very briefly about how we could extend these ideas to nonlinear problems, and in particular, how we could use these ideas, for example, to get phase retrieval in different optical problems. So before I move on, let me just say, I know that this is kind of formal because I'm wearing this funny headset and we're recording everything, but still, I'm very happy to make this as interactive as we can, given the constraints. So please feel free to ask questions, and anyone who asks a question, I'll just repeat it so that people who are logging in online could hear the question as well. So feel free to ask questions as we go along. As I said, there's many applications, I don't have to get through all of them, so I'll be happy to do one less and feel that people were actually following and understood the content. So feel free to, at any point, just raise your hand, and if anything's not clear, we'll stop and take questions. Okay, so questions so far? All right. So let's move ahead. Let's start from the very basics, right, which is the Shannon-Nyquist theorem. So we're all familiar with the theorem. And in fact, if you look at the literature and you look at what has been done in sampling theory in the past, say, 60 years since Shannon's theorem, you'll see that the basic sampling theorem has been extended in many, many beautiful ways. So I can't go through all the details, but I will give you kind of a block diagram that gives you kind of a high-level overview of what was done in sampling theory in the past 60 years. And this is kind of the outcome of work by many, many important people who have been working on these problems. So in a nutshell, what you'll find is that sampling theory has extended the basic Shannon-Nyquist theorem to any subspace model. So what that means is that if I know that my signal lies in a subspace, and it could be any subspace, it doesn't have to be band-limited, if I know my signal lies in some subspace A, then I could sample it and I could recover it using very simple filtering operations, very much like the Shannon-Nyquist theorem. And the nice thing is that it gives me a lot of flexibility. So I could look at any subspace, I could look at almost any sampling filter, and I'm still guaranteed reconstruction, where all I have to do is do a digital correction, where this digital correction has an explicit closed form solution. Okay, so I'm not going through the details, but the important aspect of this slide is that if you know that your signal lies in a subspace, then there's a very simple filtering approach that will recover your signal, given that it lies in a subspace. Not only that, but we can actually extend that to nonlinear sampling methods, which is very important in modern applications. So in many problems in optics, for example, you have nonlinearities. In communications, you have nonlinearities today because you kind of hit the amplifiers, the power amplifiers, hit their nonlinear regime because you're trying to transmit signals at high power, so they become saturated, and then you have to worry about nonlinear effects. So there's many modern applications where we have to worry about nonlinearities, and the nice thing is that we can show that as long as the nonlinearity doesn't vary too fast, where we can make this mathematically precise, but it's not so important for our discussion, then we could get very simple methods that will recover the signal, again, as long as you know a priori that it lies in a subspace. And these algorithms have a very simple form, so here's one particular algorithm where we just iterate on the linear solution. So like I said, I'm not going through the details. You could find an overview of this approach to sampling in a tutorial we wrote on this topic several years ago, and this tutorial covers subspace sampling. So it shows that if a signal lies in a subspace, modern sampling theory will give you very simple methods to sample it and perfectly recover it. Okay, so that's the good news, right? It sounds like sampling theory is already complete, right? We know how to sample anything in a subspace, and subspaces are good because that's what we typically do in signal processing is look at subspaces. So what's the difficulty, right? What's left to be done? Well, the difficulty is that there's many classes of signals that have much more structure to them than simply saying that they're characterized by a subspace. And now I want to give you some examples to convince you that what I just said before is actually true. One example that we've looked at quite extensively is this multiband problem. So in a multiband problem, you have a transmitter that transmits several bands of information, where each one of these bands is narrow, but they could be spread over a very, very wide regime. And this problem is very interesting nowadays. People look at it a lot in the context of cognitive radio that we'll talk about on the next slide. So if you look at the signal, right, obviously it's still band limited to some F max. So you could go ahead and sample the signal at the Nyquist rate, but just by looking at it, it's obvious that that would be extremely wasteful, right? Because you know that your signal is never going to occupy the entire bandwidth up to F max. It's always going to consist of several small, narrow bands of information. But the problem is that you don't know where these bands are. So if you try to characterize the signal by a subspace and use subspace techniques, the smallest subspace that will encompass your signal is the subspace of signals band limited to F max. Okay, so subspace sampling will require you to sample at the Nyquist rate. But just by looking at this, it's obvious that there's much more structure here to the problem. And the question is, how do we characterize that structure mathematically, and how do we exploit that in order to reduce the sampling rate? So like I said, this problem is very much of interest lately because of the cognitive radio problem. And in a nutshell, the cognitive radio problem comes from the fact that spectrum today is essentially all licensed, right? We know that by looking at our phone bill. So we pay a lot for spectrum. But on the other hand, if you actually take measurements, and the FCC has done that and other companies have done that, if you take measurements of the usage of spectrum over time, you'll see that there's many what they call spectral holes. So these holes could come from different reasons. Some of them are because not all of us are using our cell phones all of the time, right? Like everyone sitting in this room right now is not using their cell phone, even though they license a certain spectrum. And there's also bands that are geographically vacant, such as TV white bands, guard bands. So there's many bands that either are just never being used, or they're being used at different times in different places. And the idea behind cognitive radio is that if we were able to track this wide band and find out where those narrow bands are, then we could exploit these white spaces and use them as long as the primary user does not need them. And of course, there's a huge possibility here for income for the mobile networks, because then they could reuse the spectrum, and of course you will pay very expensively for the spectrum that you're using that you're not the primary user of. So there's a lot of interest here from the FCC and the different mobile networks. There's a lot of defense interest in this problem as well, for obvious reasons. So we've been working a lot on this problem, both with commercial companies like Ericsson and also with defense companies in Israel. Okay, so that's one problem in the frequency domain, where we see we have kind of this sparsity in the frequency domain. But there's many other problems in the time domain, and one class of problems I want to focus on, which we find in many applications, is this pulse tree model. So in this pulse tree model, you receive several pulses. They don't necessarily have to be sparse, so they could be wide and overlapping, but you have a small number of them. And what you don't know are these times of arrival. So where do these problems appear? For example, one area where this appears is, again, in wireless communication. And that's when you have multipath fading. So instead of only getting the signal that you want, you get different multipath components coming, for example, from different buildings, from a mountain, etc. So besides your desired path, you have these multipaths that you want to be able to identify and then eliminate so that you don't hear annoying echoes on the phone. The same exact problem arises in other areas, for example, radar, which we've studied quite a bit, and we'll see some applications later on to radar. In radar, these different pulses are coming from different targets. Each target will send a different pulse, where recovering the times of arrival will tell you the distance to the target, and recovering the amplitudes will give you the Doppler, or the velocity of the target. A final area that we've looked at where you see this model is in ultrasound, and that we'll talk about on the next slide. So there's many, many problems where this model appears, and therefore there's been a lot of work on this problem. And in fact, a lot of the nice subspace ideas that some of you are probably familiar with, like music and esprit, these types of ideas, actually originated from studying this class of problems. But all of these nice methods require sampling at the Nyquist rate. Now, when I say Nyquist rate here, it's worth taking a second and thinking about it. The Nyquist rate of what? So in this case, all of the methods actually sample at the Nyquist rate of this pulse. And the idea is that if you want to be able to find the time resolution, you have to take samples that the difference between them is on the order of the pulse time occupancy, which is 1 over the bandwidth, and that gives you the Nyquist rate. But if you think about it in this problem, the pulse is actually something that you transmit. Okay, we transmit the pulse. We know the pulse exactly. What we don't know are the delays. So if you look at this example, we have 6 unknowns, right? The 3 unknown times of arrival and the 3 unknown amplitudes. And we might be sampling here at several gigahertz. So we're taking millions and millions of samples to find 6 unknowns. Okay, so here I think it's even more predominant that sampling at the Nyquist rate is extremely, extremely wasteful. But again, the problem is we don't know how to sample otherwise, right? We only know how to do subspace sampling, which again forces us to the Nyquist rate. And we have the same question: how do we model these types of signals not using subspaces? And then how do we use that to reduce the rate? So let me just give one more application to ultrasound, because this has an additional twist on it. So the ultrasound problem is actually very similar to the radar problem. You send a pulse, you get reflections of this pulse as it propagates through the tissue. And what you want to find are these times of arrival, which allows you to plot one trace of an ultrasound image. And this is work that we're doing together with General Electric, which is, of course, a huge manufacturer of ultrasound machines. Now, the problem in ultrasound is that actually the environment is extremely, extremely noisy. So if you would look at one trace, you actually can't get anything. And instead, what people do in ultrasound machines is that they have an array of receivers. So they look at, say, 64 or 128 lines or traces and do a process of beamforming. So in beamforming, essentially what you're doing is you're taking the data that comes from these different arrays and you process them jointly. And in that way, you improve the SNR and get better space resolution. Now, the issue here is that the sampling rate is not even that high. It's about 20 megahertz, which is high, but it's definitely doable with standard ADCs. But the problem here is really a DSP problem, because you sample at 20 meg for all of these 128 receivers, and then you do this joint processing by beamforming to every point in the image. So for every point in the image, you jointly process this 20 meg times 128 receivers of data. That's a huge amount of data. So it turns out that actually the beamforming, the digital part, is the limiting part in these ultrasound problems. And the goal in this project was to see if we could reduce the size of an ultrasound machine. And this is actually interesting, so I didn't know this before we started the project, but if you ever wondered why ultrasound machines are so big, there's of course many factors, but one of the main factors is actually the DSP. So this beamforming is so complicated that it consumes a lot of heat. They have many processes working in parallel. And then, you know, today we try to make these chips that are smaller and smaller and smaller, but then you have 3 mechanical fans just sitting in there cooling them all down. Okay, and that's a little bit absurd, right? So we make our chips, you know, get shrinking and shrinking and shrinking, and then you have these 3 fans that just make the machine so big. So the goal in this project was to say, if we could reduce some of the DSP, not even the sampling rate, but mainly the DSP rate, then maybe we could get rid of some of these fans and shrink the size of the ultrasound without harming the resolution. So this gives you kind of another twist of the problem where the main focus is actually the digital domain and not so much the analog domain. Okay, so like I said, we're mainly focusing on sampling, but before we kind of move on to see how we do this, I do want to point out that, like I said at the beginning, there's another side to the story, and that's resolution. So if we know how to kind of characterize the structure in the data, we could also gain in terms of resolution. So one area where this is very important is radar. We talked about radar from a sampling rate perspective, but in radar you also have a big resolution limit, and that comes from the fact that you're discretizing the space when you're using digital processing methods. So what you see over here is an output of a standard radar processing technique, which is called match filtering. So it's a very simple method that people use in radar. And what I'm plotting over here is what's called a delay Doppler map. So there's 9 targets in the scene. These are these X's. And each target is marked here by its delay, which tells you the distance to the target, and its Doppler, which tells you the velocity of the target. Okay, so each point is telling you the velocity and distance of a given target. And you see here that we have 9 true targets, but the match filter, if you look at its peaks, it only recovers a small number of these targets, and many of them it recovers in the wrong place. So resolution is actually a very limiting factor in radar today, and this is something we'd like to overcome. Another area where resolution is very problematic is in optics. So essentially, from the laws of physics, if you try to view images that are smaller than half the wavelength of the wavelength you're using to illuminate the image, then you can't see those fine details. And that's just from a fundamental law of physics. So there's nothing we can do about it. It's not a technology limitation, it's a physics limitation. It's a true limitation of nature. So if you're trying to view these nanoholes, for example, then what you'll see, and this is true data that we've been working on together with collaborators at the Technion who are experts in optics, Professor Segev and Professor Cohen, then this is actually what you'll see when you try to view these nanoholes. And again, this is not a limitation of our microscope, it's a limitation of optics. So again, you see that there's a huge problem here of resolution. And what we'll see at the end of the talk is that if we use the same ideas that I'm going to introduce to capture structure in order to reduce sampling rate, we could use the same ideas to capture structure in order to improve resolution. And if you apply those techniques, you'll see that in the radar case, we perfectly identified the targets, and in this optics case, we perfectly recovered these nanoholes. So structure could be used not only to reduce sampling rate, but to get better resolution as well. Okay, so that was kind of the motivation, and now the question is, how do we do it? So the way we do that is by combining 2 ideas. One is a mathematical idea, and that's the characterization of these class of signals. And we'll see that the mathematical model is actually very, very simple. So instead of using subspaces, we're going to use what are called unions of subspaces, and I'll explain that on the next slide. So that will give us the mathematical framework, but then we need design principles as well, because like I said, we're not only interested in improving mathematical results, we're interested in building real hardware that will actually work and sample at low rates. So to do that, we're going to introduce this sampling methodology, and it's this combination of the sampling approach with the mathematical model that will give us these low-rate sampling techniques. Okay, so let's move ahead now and look at the types of structures that we're going to look at. Okay, and this is kind of where the math comes in, but it's really just one slide and it's quite simple. So like I said, we're going to move away from subspaces to unions of subspaces. Okay, and at first thought that sounds kind of tricky, but let's make that clear. It's actually very simple. So what do I mean by a union of subspace? What I mean is that the way we're going to characterize our signal is we're going to say we have a signal that lies in some low-dimensional subspace, but we don't know which low-dimensional subspace it lies in. So we have many possibilities for low-dimensional subspaces. The signal is in one of them, but we just don't know a priori in which one. Okay, so that's what's written over here. Here, for example, we have 3 options. Each one of them has low dimension. So low dimension means that each individual subspace could be sampled at a low rate, but we don't know which signal it lies in. Okay, so now let's go ahead and look at a specific example and see what that union means. So let's look at this multiband problem. So in the multiband problem, if I knew the carriers, then of course each one of these signals I could easily sample at a low rate, right? I could just take each narrowband signal, modulate it down to baseband, and sample it at a low rate. So if I knew the carriers, then the signal has it's in a low-dimensional subspace, and I could sample it at a low rate. But the problem is that I don't know the carriers. So my signal could be, for example, in this subspace, or in this subspace, or in this one, or actually there's infinitely many possibilities where the signal could lie. Now, the standard approach is to look at sums. That's what we normally do in signal processing. And if you looked here at the sum of the subspaces, what you would get is any possible signal that has energy from 0 to F max. Okay, this is what the sum of all of these guys is. And this, in fact, requires you to sample at the Nyquist rate, right? Because it increases the dimension. So sums, which is what we're used to do in signal processing, increase the dimension and bring us back to the Nyquist rate. Whereas the union allows us to capture this low dimensionality. The union allows us to say we're still in a low dimensional space, but now we have another parameter of uncertainty saying I just don't know which subspace I'm in. Okay, so this is really key because everything else is going to be based on this. So this is a good time to ask if you're not feeling comfortable with this union model. Any questions? Yeah. Okay, so I was asked to go back. Yeah? Mm-hmm. No, because if I don't know where the carriers are, then I have to go through, I don't know where the carriers are. So I could use bandpass filters, but then I have to use them all the way up to the Nyquist rate, and I'm sampling at the Nyquist rate. So there, as far as I know, there's no method that will allow you to sample this at a lower rate.
So the assumption is now in the signal space we're going to construct, right? It's not on the data.
No. So let me repeat the question. The question was, in all of the examples we're looking at, this assumption of structure, where is it? The structure is on the signal that we want to recover. Okay. So this is the union model, and now let's go ahead and see how we actually use it to reduce the sampling rate. So, okay, I was asked to go back again. I'm sorry, I'm just repeating it because he asked me to repeat for the sake of people on the...
You just imagine you have a signal which is a wide band from 0 to F max. and the signal of interest can lie anywhere in that band of 0 to F max. And we started with the problem that, okay, now you want to recover such a signal, you need to sample that at 2 F max. What I'm thinking is if you had a 0 to F max considered as a bank of uniform filters, uniform filter bank, you don't know where the carrier is, but you construct a n banks, let's assume n banks between 0 to F max uniformly, then doesn't it mean that the output of those analog filter bank can be sampled by Fs by n?
Okay, let me repeat your question. So the question is, if I take the band from 0 to F max and sample it with a uniform filter bank, could I save on sampling rate? And the answer is no, because the output of each one of those filters, I could sample at Fs over n, but I have n of them. So altogether, my total rate is still Fs. I want to get rid of that total sampling rate. Okay, so hopefully I've convinced you that the union model gives me a low-dimensional representation and that there's no other way of doing that. And actually, the questions are very helpful because I'm sure that other people were thinking the same thing. So it helps kind of emphasize that standard methods will not allow you to reduce the rate. So the question is, though, how do I reduce the rate? So let's look at the stream of pulses, right? Hopefully I've convinced you that if you describe this by a union, then you have low dimensionality. But then, okay, let's say you're convinced and you say, great, so I'm going to sample this at a low rate. But if I just take low rate samples, then I'm going to sample zeros, right? I mean, with high probability, most of my samples are not going to be informative. And the same thing is true with the multiband. So if I only sample certain bands, if I take that uniform sampling bank, filter bank idea, and I say, okay, I'll only look at specific outputs, then with high probability, I'm going to be missing my signal. So how do I reduce the rate? Well, the idea is actually very, very simple. So the idea is that we actually alias or smear our data before we sample it. Okay, and this is counterintuitive because we always learn that we're supposed to avoid aliasing. But here we're intentionally introducing aliasing. So for example, if you look at the stream of pulses, what we do is if you put these pulses through some sort of low-pass filter, we're going to do something more sophisticated, but just for the sake of the idea, you could think of a simple low-pass filter. Then each one of these pulses is now going to be smeared. And now when I sample it, my samples will actually be informative. They're not going to be zero. They're going to be giving me energy from the signal. The same thing in the multiband problem. If I alias all of my data, if I somehow manage to get all of my data down to baseband before I sample, then I could go ahead and sample in baseband, and my samples will be informative. So aliasing helps me reduce rate and still have informative samples. Of course, the problem is that you could say, okay, great, now you got informative samples, but they're all mixed up, right? They combine the data from all of the options. How do you go back and locate where your pulses were? Well, that we're going to do on the digital domain. So on the analog domain, I'm going to reduce rate by aliasing or projecting before I sample. And then we're going to come up with recovery algorithms on the digital side that allow me to get back this lost resolution. Okay? So this is really the main idea. So on the analog side, what I do is, this is the most important bullet. So what I do is, I sample in a way that my data contains combinations from all of the possible subspaces. Okay, remember again this union model. I have many, many possibilities of subspaces. I make sure that I sample in such a way that all of my subspaces are combined into my data stream. I alias the subspaces before I sample. Then on the digital domain, I'm going to have two steps. The first step is to identify the subspaces involved. So it's going to be a detection step, not a reconstruction step. And we'll see that the fact that we first do detection will allow us to do things at very low sampling rates. So I'm never going to have the Nyquist rate in the system. I'm first going to detect which subspaces were actually in my data. And the beauty of that is that once I know the subspaces, we go back to the beginning of the talk, right? Remember we said at the beginning of the talk that subspace sampling is a solved problem. So if I know where my subspaces were, then I could use standard methods to recover at low rates. It's an easy problem. So all I need on the digital side is this additional identification step. And if I could do this at a low rate, then my whole algorithm, my whole sampling and recovery algorithm will work at a low sampling rate. So how do I do that identification step? That's kind of the only piece missing yet. Here I could use two classes of ideas. Either I could use subspace methods. So in the context of array processing, for example, people have developed very sophisticated different subspace techniques that allow you to identify subspaces. Okay, so that's my problem. I have this data that contains combinations from subspaces, and I want to identify the subspaces. Well, that's a standard problem. I could use standard results in order to identify the subspaces involved. The other set of ideas I can use, which is more recent or more modern, are these compressed sensing ideas. So just out of curiosity, how many people are familiar with compressed sensing? Okay, quite a few. So those of you that are not, don't worry, and those of you that are, don't worry either. I'm not going to talk too much about compressed sensing. But we could also use compressed sensing ideas, and I'll talk about that a little bit on the next slide. Now, this is all when the sampling is linear. When the sampling is nonlinear, we could extend the nonlinear methods we've developed for subspace techniques in this context as well. Okay, so the important thing is that we leave the subspace structure and we just add an identification step. And because both steps have been studied independently in the literature, we could kindly, smartly combine results that are already available on the DSP side, as long as on the analog side, we've sampled in a way that we've properly aliased our data. So that's the main idea. Okay, so let me just say two words, a very compressed two words about compressed sensing, just for the sake of people who are not familiar with it. So compressed sensing, in a nutshell, deals with vectors that are very long, but are sparse, meaning they only have a few non-zero values. And the idea behind compressed sensing is that if you have a sparse vector, you could recover it from a small number of measurements. So if this vector, for example, was of length 100, but has only 4 unknowns, you don't need 100 measurements to find it. You only need on the order of 8 measurements, 2k, where k is the number of non-zero values, in order to recover it. And there's many algorithms that have been developed in recent years in order to allow you to do the recovery in an efficient way. So how does this relate to what we're doing? So we don't have a standard compressed sensing problem because we have analog data and subspaces, etc. But we can use compressed sensing ideas on the subspace domain. So we can think of our problem as having a set of possible subspaces where only a small number of these subspaces are actually active. And the measurements that we have are combinations of these subspaces because we've aliased our data. And therefore, we could use the same ideas of compressed sensing in order to identify the sparse number of subspaces that are active in our data. Okay, so that's the relationship and how we exploit compressed sensing in our developments. Okay, so the only thing left is to talk about how we actually do the sampling. So all I said is that we have to sample in a way in which we alias the data, but there's many ways to sample in an aliased way. So in addition, what we want to make sure is that our methods are going to be robust to noise. And in order to do that, what we've done is we've actually developed bounds on how well you could estimate a signal given a specific sampling rate and assuming that it has a particular structure, in our case, a union of subspace structure. So I'm not going to go through the technical details here because actually they're quite involved. So we're all familiar with doing kind of, let's say, Cramér-Rao bounds when we're looking for a finite set of parameters. But here we're looking at analog signals. So the Cramér-Rao bounds become much more involved technically. We have to develop bounds for analog signals. I'm not going to go into the details, but the nice thing is that the result is very simple. So we're not actually so much interested in the bounds. What we're interested in is the optimal sampling technique. So we want to find a bound, and then what we want to say is what is the optimal sampling method that will minimize my bound, that will allow me to get the smallest possible error. And the nice thing is that it turns out that under certain technical conditions, which we satisfy in all of the problems that I've shown you until now, the optimal sampling method turns out to simply be sinusoids. Okay, so if you alias your data with sinusoids, you're guaranteed that that is the optimal thing to do in terms of these Cramér-Rao bounds. Okay, so that's actually really cool, right? Because sinusoids are easy. We know how to do them. So that's almost true. The problem is that if you would actually just apply those results, you would need many, many sinusoids. So if you think about the multiband problem, suppose we have 12 bands, we would need, let's say, 24 sinusoids. Well, that starts to become hard to do in hardware, okay? So trying to get 24 VCOs on a piece of hardware, they have to be completely synchronized. It starts becoming a little bit tricky, okay? So we've tried to do that, and you could do that up to 8 or 10, but beyond that, you already have hardware issues. But the nice thing is that now we could exploit mathematics again that come and help us. And the nice mathematics is that if you take a signal, any signal that's periodic, then you could write it in terms of a Fourier sum, which means that a periodic signal actually has infinitely many sinusoids in it for free. So now all I have to do, instead of multiplying with many, many sinusoids, all I have to do is multiply with one periodic function, and it's as if I'm multiplying with many, many sinusoids. Okay, so this is already really nice because this already allows us to do something very practical. We take our signal, we multiply it with a periodic function, or if we want some flexibility, we use several periodic functions, but we could use a small number because each one already has many sinusoids. So the most we use is 4. And then for free, we're as if multiplying our signal with many, many sinusoids. And then all we have to do is low pass the signal, sample it at a low rate, and we're done. And we're guaranteed that we alias our data in the optimal way. And this scheme works for all of the applications we've seen. So this is a generic structure for union of subspace models. We don't have to go ahead and change the structure for every possible application. Okay, so that's the main idea. Now let's go ahead and look at some applications. So let's start with this multiband problem. To remind you, we have a signal that has several bands of information. Each one of them could be anywhere on the spectrum. They might be changing in time. We don't know where they are, but each one of them is narrow. So let me skip through some of the mathematics in the interest of time and just go ahead and actually show the scheme. So this is just an example of the general scheme that we've seen specified to this case. So what do? We take our signal, we multiply it with a periodic function. Now let's just go ahead and understand why that actually does the aliasing. So I told you it does, but now let me convince you. So we know from basic Fourier series that if we multiply our signal with a periodic function, then in the frequency domain, we're convolving the signal. And a signal, like we've seen already, that's periodic in the frequency domain looks like a sum of delta functions. Now, if you convolve a signal with a delta train, what are you doing? You're aliasing. That's the definition of aliasing, right? Because convolving with a delta train means you take your signal, right? Then you shift it to the right, you shift it again, shift it to the left, shift it again, and sum everything up. Well, that's the definition of aliasing. So what you're going to get at the output is something that looks like this. Now, in fact, you'll get this all over the spectrum. So basically, you're aliasing all of this data all over the spectrum. But we don't need it all over the spectrum. We only need it in the low-pass regime. So we filter it, we sample at a low rate, and we're done. Here's our alias data. Okay, so it's very, very easy. Now, to recover, like I said, we use these compressed sensing tools. So I'm going to skip the recovery because it really follows from compressed sensing ideas. Because not everyone here is familiar with compressed sensing, I'm going to skip this part, and we could go back to it, whoever wants, after the lecture, just for the interest of those people who are logged in and need to log out after 45 minutes. So this is the main idea. Here's the hardware that we've built to actually implement it. Like I said, it's very easy, and the reason that I could say for sure that it's easy is because we did it, okay? So I'm a DSP person, not a hardware design expert, and me and my student were able to build this in the lab, which of course means that if it was too difficult, we wouldn't be able to do it. So that's kind of the ultimate proof that it can't be too hard. So what you see over here are 4 branches. These guys are the multipliers. And this over here is a digital signal that we create as our periodic function. So our periodic function is just a bit flip sequence. This creates the bit flip sequence, and then you see over here there's 4 outputs that just go into each one of these modulators. So it's the same signal with different shifts that are input into this analog structure. And that's it. And this is the filtering, and at the output what you're going to get is that alias data. Okay, so here's what it looks like if you have, for example, 3 different signals. So they're arbitrary modulations. It doesn't matter how they're modulated. They have arbitrary carrier frequencies. After you go through our prototype, this is what you see. So you see all of this data alias down to baseband. And after you go through an FPGA that implements our digital recovery technique, you get each one of the signals separately. And all of this is done at the low rate. So the DSP is working at a very low rate as well. Okay, so we've had several demos of the hardware where we just allowed people to come in, play around with the modulations, play around with the carriers, and show them that this really works in real time. So those of you interested, there's a lot of there's a lot of info on my webpage. You could go ahead and look at some of the demos. There's some recordings there that you could go ahead and take a look at. Okay, so the exact same method is going to work now with all of the different problems we've talked about. So we've applied it to these pulse stream problems. I won't go again through the math because it's exactly the same. We could apply it to the pulse stream problem even when we don't know the pulse shape. In that case, the analog side is the same. The digital side has another additional twist to it that recovers the pulse shape. But again, everything is done from the low rate samples at a low rate. And like I've said also, we could apply the same idea to multipath identification. And this is some work that we're doing together with National Instruments to actually build a communication scheme that uses these low rate ideas to recover the multipath medium. But all of it uses the exact same hardware that we've seen before. So finally, I want to talk about the radar application, and this is slightly different because here we're interested in resolution. So remember we said at the beginning that if we could exploit the structure, we can use that to increase resolution. And we do that by using the exact same method. So we use our same recovery method. Not only are we getting better resolution, but we're doing it at a low rate as well. Now, if you have high SNR, so if the noise is not too bad, then you get perfect resolution, just like I've shown you at the beginning of the talk. Okay, so there's nothing additional here. It's using the exact same techniques. But of course, all of these methods start becoming much less powerful once you have noise. So they're going to be obviously less robust to noise because you're aliasing all of the data, and therefore you're also aliasing all of the noise. So the interesting question, particularly in radar, is how low could we go and still get meaningful results? So we've developed hardware for the radar problem. The reason that we have a separate hardware and we don't use the same prototype I showed you before is because here we do take specifics of radar into account. So this hardware was developed specifically for the radar problem. And again, we had a demo of this at NI. This was done together with NI, where again, we allowed people to come in, input arbitrary radar pulses, and see the recovery. So what I'm showing here is recovery from our demo for a specific scenario. And this was a very tough scenario. So in this case, the SNR was minus 25 dB. Okay, that's a really low SNR. So what you see in that SNR is that when we use standard methods like match filter, we only get 40% detection. Whereas when we use our method, we get 80% detection. So we're not getting full detection, but we're at minus 25 dB, so we can't really hope for full detection. But the nice thing is, and that you'll see on the next slide, is that as soon as we move up a little bit, so when we get up to like minus 22 dB or minus 21 dB, we already have perfect detection. So as long as this radar is working in an environment over minus 20 dB, we can get perfect detection at very, very low sampling and processing rates. So this is important to keep in mind. All of these methods are going to be sensitive to noise. If the noise is too strong, they're going to lose their ability to give you perfect recovery. But as long as that threshold is reasonable for your application, then these techniques are viable. And again, this is real data, and minus 20 dB is pretty low. Okay, so at least for the radar companies we're working with, they're happy with minus 20 dB. And we get a very big savings here on the sampling rate and on the processing rate. Okay, so here we're using about 1/10 of the Nyquist rate. Okay, so let me just say 2 words about the ultrasound, because I think we're running. How much time do I have left? 5 minutes. Okay, that's fine. So let me just say 2 words about the ultrasound. So the ultrasound is very similar to radar, but here we have the additional challenge of the beamforming process. And what we were able to show is that we could do all of that beamforming in the low rate domain, meaning I take the samples in the exact same way I've shown you now, and I could do that beamforming process from those low rate samples. So I won't go through the derivations. They're here on the slide, so maybe those of you that are interested, we could stay after we log out and continue to talk specifically about this application. But we do the sampling the same way. We just use sophisticated DSP ideas in order to combine the data and do the beamforming in the low rate. And the nice thing is that what that will give us is it will give us very, very good resolution, very good SNR, all done at a very low sampling rate. So let me just show you, let me kind of skip the mathematical derivations and just show you the end result. So this is the end result. What you see over here is the standard image that you get. Okay, now at the beginning I showed a baby, so people look at this and try to find the baby. There's no baby here because this is a cardiac image. Okay, so the beginning was just to kind of get you interested in ultrasound. This is real data from GE. And actually, cardiac imaging is a very important application because speed is very important there. So if you could speed up the DSP, not only are you saving on power, but for cardiac imaging, that's actually crucial. And that's why we looked at cardiac data in this application. So this is true data coming from a consenting volunteer. And what you see over here is what you get from standard imaging. And this is what you get from our methods. So you see that all the strong perturbations, which are the important information in this application, are completely preserved. But here we're sampling at about a 10th of the Nyquist rate, which is nice. But what's more important is that all the beamforming is done at that rate. So the savings is kind of that 10th to the power of the number of arrays times the number of pixels at which you do the beamforming. So there's a huge savings here in terms of the DSP. Okay, let me just wrap up by saying 2 words about the nonlinear techniques. So until now, we assumed that everything is linear, but we can combine these same ideas with nonlinear methods. And here, basically, what we have to do is extend compressed sensing to nonlinear sampling techniques. So compressed sensing always dealt with linear data, and now we've basically looked at an extension of compressed sensing to the nonlinear domain. And once we could do that, we could just combine that with the subspace ideas that we have and merge them to be able to do all of this from nonlinear samples. So again, the power is by looking at this union of subspace models, we can use results that we've already developed for the subspace ideas. So if you put that together, and let me skip the math, you go back to the application I've shown at the beginning. So even though this is the data that we get at the output of the microscope, this is what we get after applying our nonlinear compressed sensing method by exploiting the structure in this data. So wrapping up, what we've seen is that we could compressively sample a wide class of analog signals. We could do this not only on paper, but we actually do this in practice. We have robust hardware that will allow you to do this. The important thing is that this allows us to treat a very, very broad class of signals in a unified way. So it's not like we have to rederive everything for every specific application. But really, maybe the most important thing that I want to say is that this is very much work in progress. So we've done what we've done. Maybe there's better ways of doing it. Maybe there's more applications to look at. I'm sure there are. So really, our goal is to hopefully interest people in these ideas. But then again, if we really want to make this into a technology and have an impact on industry, I think we need many more people to work on this, and people that are coming from different applications. So what we've discovered when we've been working on these problems is that each application has its own know-how. There's different things that people care about in specific applications. And it's not enough to just have some generic mathematical structure that kind of take care of different problems. You have to really dig down into the specific applications and modify the ideas and the hardware in order to meet the designs and the specs of that specific application. So we've been trying to do that with the specific applications that I've shown so far, and hopefully others will get interested and join this effort. And I think that collectively, if enough people get interested and work on this, then we could really kind of think of a new paradigm where we sample and process by exploiting structure and data and get much, much lower rates than what we see today in existing technology. So just to wrap up, I've skipped all of the technical details. Those of you who are concerned that maybe this is all just kind of hand-waving, I promise you there's a lot of math. So you can go ahead and look at the papers and find the math. Those of you that were satisfied with the hand-waving, you don't have to look at those papers. You can also find a lot of info on our website. So we try to put the code and the different ideas on our webpage, so you could find a webpage dedicated to sampling where a lot of the data appears. And there's also a lot of the information in a book that recently came out that we put out on compressed sensing and has some chapters on these analog ideas. So finally, thank you very much for your attention, and I'd be happy to take questions.